Hey, welcome back to today's lesson. We're actually starting our next unit today of what's going on with the periodic table and some chemistry stuff. We'll finally get to do some real chemistry. I'm supposed to talk about a lot of physics stuff. So anyway, this particular unit here is about chemical formulas, chemical symbols, brief introduction to the periodic table, and just kind of learn some basics about how the periodic table is arranged. So it should be pretty quick and easy, but well, maybe you'll learn something new. In terms of the periodic table, when they first started doing the periodic table, can you imagine if you had to do a chemistry class when these were your symbols of the elements? In the early days, they used different symbols that looked a lot more like alchemy, actually, where they were trying to transform one element into the other. So this was a long time ago, back in the 1700s or so. But the dude over on the right, Dalton, the one that says elements, starts to look kind of like a modern periodic table. It's at least got some words out there that we recognize. But again, the symbols look very, very different. So they kind of started to realize that we needed some different patterns. Because as you can imagine, trying to represent what compounds looked like with all of these different symbols got a little clunky. Imagine doing your homework with these as your symbols for writing formulas as opposed to the modern system that we use today. So especially that one on the bottom left, number 20, dang. So we got some other ways that we've come along with in the last few years, about last 200 or so years. Started off with this guy named Dmitry Mendeleev. I'm not going to test you on his name, but he's actually the father of the modern periodic table. He's Russian, as you can kind of tell from his name. But it starts to look, his tables start to look a little bit more like what we would kind of picture a periodic table to look like. And if you look closely at that, you'll start to see some things that you recognize. Big ideas here, some things that are very important to this, is to take a look at the symbols that he's using. One of the things that's really important is that even though Russian is a very different language than English, they used all of the same letters that we do. They didn't use the Cyrillic alphabet. And so with these, each element had its own unique symbol, and those symbols all have a capital letter to start with and a lowercase letter if there's a second letter to it. So if there is a second letter, it's always lowercase. First letter is always uppercase. So important rule to make sure that you start to get into the habit of doing that. One of the reasons why they started to do this is as chemistry became a science, started to realize that people around the world were calling the same elements by different things. And so this, I just threw this in here as an example of a Chinese periodic table. And even though the names of the elements are in Chinese, that's what those characters are that's on there, the symbols for every element is still written exactly the same in every language around the world, which is actually pretty amazing that any two chemists can talk to one another, at least through the language of chemistry, and know that they're talking about the identical symbol. So it's a universal language that we all can use. So again, some basic rules. I threw a couple examples up here. Each element has its own unique nickname. We call those nicknames chemical symbols because writing out the full words is really long. And again, other languages have different terms for those things. They're always one or two letters with a brief exception that I'll mention in a second. Usually the first letter is the letter from the element's name. Second letter is usually somewhere in the name, but that's not always true. But again, the key idea here is that the first letter has to be capitalized. Second letter has to be lowercase. There's a few cases where there's three letters, like the one I have kind of written in there, U, U, Q, and some other ones. For the proposed elements, they have a three-letter naming system, but that's pretty unusual in terms of what we see. So one or two letters, capital and lowercase. So if you've looked at the periodic table before, spent some time trying to spell your name or write whatever words you're trying to write with them, you'll notice that some of them don't really seem to match. So I threw some of the big ones up on this particular screen, where the element names, like sodium has S-O-D-I-U-M in the name, and the symbol is Na. What the heck is that? Almost always, the reason why they don't match is because the English name doesn't match the Latin name. And when Mendeleev and those guys came up with the original chemical formula symbols, they were using the Latin names from it. So the Latin name for sodium is natrium. The Latin name for potassium is kalium. Silver is argentum. Lead is plumbum. Tin is stannum. Iron is ferrium, gold is aurum, and copper is cuprum. So again, I'm not going to test you on those names, but in terms of there's a reason why they don't match, and that reason is pretty much always Latin. And even if you go to other countries, like you go over to Europe or you go to Russia or China, they'll have their own names for the different elements. The symbols are identical, but the words that they would use to describe them are usually words from their language. So again, the symbols themselves are the universal part, not necessarily the words for the names. So kind of the next step from this is, once we know what the symbols are, really the important part is not just identifying the elements, it's actually starting to identify reactions and compounds as things are starting to bond together. And again, back in Dalton's time when he used these crazy weird symbols, I can't even imagine trying to draw out all of the reactions with circles and pluses and all these different crazy signs, like that one on the right, aluminum potassium, or potassium aluminum sulfate. It would be difficult to do it that way, kind of clunky. So there's a new system that we've come up with that actually represents chemical compounds with the modern symbols, and a combination of symbols and numbers. So when you've got writing the formula for a compound like water, H2O, you always list the elements that are present in there. So H is the element for hydrogen, or the symbol for hydrogen. O is the symbol for oxygen. So you list each element that's present. Typically, if there's a metal present, the metal will always go first. That's not 100% of the time, but if you're starting to write formulas, that's a good place to start. Organic compounds sometimes are written a little bit weird. So on the screen in front of you, the bottom one, CH3COOH, it's like, why didn't they combine all that out? Because that's an organic compound. So that's more giving us a picture of how those atoms are bonded. Kind of like what order. It's carbon and 3 hydrogens and carbon and then an oxygen, then an oxygen. So anyway, you don't need to worry about why that is, but if you see it, don't freak out about it. So the second part of any chemical formula is some little things called subscript numbers. And subscript numbers tell us really important information about the actual structure of the molecule. So in this case, it was going to tell you the number of atoms of each element that are present. So when we have H2O, that little 2 in the middle tells us there's 2 hydrogens, and there's nothing after the oxygen, so that tells us there's 1 oxygen that's present in there. So keep in mind there's a couple of rules for writing these that I'll kind of get to in a second, but they're always little subscripts. Sub means below, and tiny, so it's kind of a little half-size number that drops down below the line. When you have a number like H2O, that 2 only applies to the element in front of it, which is obvious in H2O, but in like compounds like H2SO4, it may not be as common, or may not be as easy to understand that last 4 only applies to the oxygen that it's touching. It does not apply to the sulfur that comes right before it. So again, it applies to the one that's right after it. So if we're trying to do more complex things, we sometimes have to identify that there's groups of atoms that are kind of stuck together in their own unique way. These are called polyatomics. I'm not testing on that word yet. We'll get there later. But these little groups, like in that top left one, OH functions as a little group, or in the top right one, the NO3 functions as a group. So with those, we put parentheses around those groups to indicate that those guys are kind of have a little special status. So with these, now when we have subscript numbers, we would have to kind of be careful about where we put them. So a subscript number like in MgOH2, where the 2 is outside the parentheses, that means there's 2 OHs. There's an OH and then there's another OH. So that subscript only applies to the set of things inside the parentheses, not just the element it's touching. So in BaNO3 we've got 2 different kinds of subscript numbers in there. The 3 that's inside the parentheses only applies to the oxygen, but the 2 that's outside the parentheses applies to that whole group. So there's 2 NO3s. There's an NO3 and another NO3. And I know that gets a little bit confusing. We'll work on some more examples in class. And then the last thing that's on this particular screen is coefficients. If we put a number out in front of a compound, like 2AlPO4, or at the very bottom 2CuMnO4, ugh, crazy, that number is a multiplier. That means I have 2 of everything that's after it. So a little bit different. So just as a quiz, take a second and take a look at the one that's right in the middle of your screen. Starts with NH42, and see if you can figure out how many elements of each, how many atoms of each element are present. Hit pause, take a look at it, and then I'll say what the answer is. Did you actually pause it? I don't think you did. So anyway, with that one, each element, in terms of nitrogen, hydrogen, carbon, and oxygen, those are the 4 elements that are present. In the nitrogen, there's 2 atoms of nitrogen because there's a 2 outside that parentheses. In the hydrogen, there'd be a total of 8 atoms of hydrogen because you've got an H4 and then a second H4. So that's a total of 8 hydrogens. There's 1 carbon, that's a pretty easy one, and then there's 3 oxygen. That's a pretty easy one as well. So again, it's a little bit tricky. We'll work on some more examples of this inside. So the big idea here, parentheses indicate groups of atoms called polyatomics. And then if you have a subscript outside a parenthesis, then that subscript applies to everything that's inside of that group, kind of like in math class when you're distributing. Okay, a couple things not to do when you're writing chemical formulas. So when we write them, chemical symbols, you always keep them in the same order. You never rearrange them and write them in a different order. Don't change upper and lower case. Sometimes it can get really confusing as letters start to overlap, so be a little bit careful with that. With our subscript numbers, always write them down and below, between the two elements, or touching the element that it refers to. Don't ever write it up above like an exponent, and don't ever write it full size. They always need to be small. Second thing, when you've got parentheses and coefficients, the important rule here is you never distribute it when you're writing a formula. I may ask you the total number of atoms, but you would never change the formula. So in that middle example that's on there where it's got NH420, you would not go through the process of writing it out differently as N2H8O. That would be just more of an accounting kind of an issue. So you always want to leave those formulas kind of the way they are. If there's parentheses there, leave them in there. It's kind of an important piece. All right, so brief introduction here. It's definitely going to take some practice to do these, so you want to find some examples and kind of practice doing this. But what you should be able to do as a result of this little quick introduction would be to tell me that chemical formulas or chemical symbols are a universal language, that those symbols are across the world always identical, that there's basic rules, capital and lowercase letters, that sometimes they don't match in terms of unusual symbols based on their old school Latin names, or names from other languages, usually Latin, that you should be able to write some chemical formulas or tell me kind of how to write them. You're not going to have to come up with a chemical formula on your own, but you should be able to sort of interpret a chemical formula in terms of the number of atoms of each thing that's there. And then especially the ones that are complex, the ones that have parentheses or coefficients, that you can carefully apply those coefficients or those subscripts to just the right thing. So a coefficient would go all the way across the molecule, as opposed to a subscript number on parentheses would apply only to that piece. So we'll do some examples in class and practice this a little bit more. But this is just your kind of brief introduction to chemical symbols and formulas. Hope it gave you a good overview. See you in the next one.